I am Baiju, presenting our ongoing work on simulating oceanic abiotic radiocarbon using NEMO forced with the GRA forcing. This figure illustrates the production of radiocarbon and distribution throughout the Earth's reservoir. The radiocarbon is naturally produced in the upper atmosphere by cosmic ray interaction with a nitrogen atom, where it is rapidly oxidized to the CO2 and becomes available for incorporation within the global carbon cycle, and it decays with a half-life of 5,700 years. This natural radiocarbon is very useful in understanding the deep ocean circulation because its abundance in the deep ocean is a direct measure of time elapsed since the water was in contact with the atmosphere, which is called the ventilation. This oceanographic C14 are typically reported as delta C14, which is expressed in per mil units. It is the ratio of C14 and C12 of a sample related to a standard, with corrections applied to account for fractionation effects. Nuclear weapon testing added a large pulse of C14 to the atmosphere. This figure shows the compiled records of historical data sets of annual mean values of atmospheric radiocarbon from Graven et al. Atmospheric delta C14 decreased by approximately 20 per mil between 1850s and 1950 as a result of fossil fuel emission after the Industrial Revolution. Then it is increased rapidly from the mid-1950s until the mid-1960s during the period of intense nuclear weapon testing, which has reached more than 600 per mil in the 1964 and 1965. And in 1963, nuclear tests were prohibited by the Test Ban Treaty. And but however, there are still some tests. After the peak in mid-1960s, delta C14 decreased at a nearly exponential rate as the bomb C14 mixed into the ocean and terrestrial biosphere, and that can be utilized as a physical and biogeochemical tracer in the terrestrial and marine settings. For example, the flux distribution and inventory of bomb C14 in the ocean can be used to constrain rates of acid gas exchanges, and exchange between shallow and deep ocean C14 is widely used in model evaluation. A number of oceanographic surveys have been conducted since the early 1970s. However, the low sampling frequency, they are unable to capture the precise timing and amplitude of the bomb pulses. Therefore, we implement the abiotic radiocarbon in NEMO, ocean-only model, compare with the delta C14 observation data, and understand how the radiocarbon is distribution is affected by fixed versus variable GRA forcing. The model we use on NEMO, the current version uses 362 longitudes and 332 latitudes and 75 vertical depths, and the vertical depth thickness increases exponentially with depth. In the model, the abiotic DAC and dissolved inorganic carbon and corresponding radiocarbon isotope are the model traces for other model traces from OMIC based on the OMIC protocol. And the abiotic carbon is used because it is simpler to implement. Also, the delta C14 includes a correction of isotope fractionation, and other abiotic impacts on delta C14 are thought to be very small. And the model is forced by GRA 55 do forcing, which is available for the period 1958 to 2070, and we use this repeat cycle to start from 1815. We have also used the GRA nuclear forcing a 12-month period from 1st May 1990 to 31st of April 1991 in the GRA 55 do record that are most neutral in terms of major climate modes of variability like SAM, Southern Ocean Index, and Oscillation Index, and North Atlantic Oscillation. The model uses historic atmospheric radiocarbon from 1850 to 2017, which includes natural radiocarbon and bomb radiocarbon. Also, the model has been initialized with abiotic dissolved inorganic carbon and the corresponding C14 from OMIC BGC initial condition based on GLODAP. We initialized the transient simulation from the period for the period 1850 to 2017 from the end of his spin-off from Alice. So we got 4 simulation. His simulation that simulates total C14 with the transient atmospheric CO2 and delta C14 and the GRS cycle forcing. And the fixed simulation that simulates natural C14 with the fixed atmospheric CO2 and the delta C14 at 1850 values with the JR cycling forcing. And we forced the models with the JR nuclear for the fixed and the transient atmospheric CO2 and delta C14 as HIST NYF and fixed NYF. And the difference between HIST and HIST NYF and fixed minus fixed NYF simulation indicates a change in radiocarbon distribution caused by change in ocean dynamics and air sea exchange due to variable forcing. Now we show the observational records in the Pacific and Atlantic. A number of oceanographic surveys have been conducted since the early 1970s, providing an indication of large-scale isotope distribution in the modern oceans. Here I show the 2 transect, one along the 150 west in the Pacific, the P16 transect, and one along the A16 in the Atlantic from 70 north to 70 south. It is plotted against the potential density because comparing the changes along the potential density rather than depth eliminates most of the effects of vertical water mass displacement by intermittent deepening and heaving of potential density layers. So this allows the comparison of C14 in the same water mass between 2 data sets and the time periods. The observation records are compiled for the periods 1990s, 2000s, and 2010s for better coverage. And the black dots here shows the sample locations. In the 1990s, GLODAP has more than 100 per mil delta C14 in the upper ocean and are more negative than minus 200 per mil in the deep ocean, and consequently there is a large strong vertical delta C14 gradient. By 2000s, the surface values reduced to less than 80 per mil in the upper ocean, which is further reduced to less than 40 per mil in the 2010s as a result of decreasing input from the atmosphere as shown here between 1990s and 2000s. Now, comparing the model, simulated total radiocarbon from his simulation in the Pacific shows that the model captures large-scale structure and range of delta C14 values both spatially and temporally. Here, the model is sampled for the same coverage as in the observation for the comparison, and the maximum D14C is found at roughly 20 degrees in both hemispheres. Vertical gradients are weak, south of 55 south, north of 55 south, the high at the surface, and decreases sharply along at 26.5 potential density layers. A strong delta C14 gradient occurs between subtropical and subantarctic fronts. Looking at the model bias, looking at the model biases changes over time in the shallow reservoir. Model underestimates with approximately minus 20 per mil in the shallow depths at low and temperate latitudes in the 1990s. Biases then reduced to minus 10 per mil in the 2000s, but the bias then turned to positive in the 2010s. And at the same time, model overestimates at high latitudes, indicating that the model is not efficient in transport and that accumulates too much of radiocarbon near the surface, causing high delta C14. And the deep ocean model simulates more radiocarbon than observed, indicating that in the model model is too efficient transfer of radiocarbon into the interior ocean. Similar way that analyzing the model's performance in the Atlantic shows that the spatial and temporal structures are well captured in the Atlantic Ocean as well, especially the deep penetration of radiocarbon in the North Atlantic, and there is a strong north-south gradient in the deep Atlantic. Looking at the biases, the model underestimates the North Atlantic in the deep ocean, but the biases decreases with the time. Also, there's a positive biases in the south of 40 south, which is increasing over time. Now, it is worth to know that change in delta C14 over the recent decades because the difference in transport between the model and the real ocean yields strong differences in the distribution of delta C14 in the ocean interior, especially when considering the changes in delta C14 in the last 3 decades. Since we got observation records in the 1990s, 2000s, and 2010s, we could compare the rate of change of delta C14 over the decades. Here I show the decadal changes from 2000s minus to the 1990s and 2010s minus 2000s for the from the observation and his simulation in the Pacific along the 150 west. So the change in delta C14 is largely negative in shallow water and positive in deep water. Deep water, switching the sign at roughly sigma theta 26.5. In the tropics, the change in C14 switched from negative to positive at slightly lower densities of 26, while in the high latitudes, the negative changes occurred in denser layers of sigma theta 27 that are exposed to the surface. Similar biases in the 2000s and 1990s were found in a curve in a study Graven et al., while the CCSM is overestimated. The latitude average of the change shows that both model and the observed records are in good agreement, but with a slight biases changes. Looking at the recent changes in 2010s and 2000s, it is changes are reduced. Also, the change occurs rapidly in the observation, but in the simulation, it is too weak in the shallow and deep reservoir, indicating that the model is too efficient at dispersing C14 into the deep ocean. The latitude average of in the recent decades shows that the deep ocean changes in delta C14 are negligible in both observation and simulation, indicating that the most deep ocean C14 is mostly saturated. Similarly, the changes in delta C14 over the decades in the Atlantic Ocean shows that the rate of change is slightly underestimated in the model. On the model, also changes occur rapidly in the observation than in the model. Also, the change in the 1990s and 2000s, the change in delta C14 are largely negative in the shallow water and positive in the deep water, switching the sign roughly at sigma theta 26.5 in the model, but it is 27 in the observation. Density layers separating shallow and deep reservoirs shift to higher densities in 2000s and 2010s. We have simulation forced by JRA neutral air forcing that simulates steady state ocean. Therefore, the difference in JRA and JRA neutral air forced simulation provide information on the change in delta C14 distribution due to the difference in air-sea exchange and interior ocean dynamics. Here we show that the change in delta C14 distribution due to the forcing differences in the Pacific along the 150 west translate between the HIST minus its NYF simulation and fixed minus fixed NYF simulations. It indicates that JRA cycling leads to more the C14 in the lower thermocline of the Pacific and less in high latitude shallow ocean. Both natural and born C14 contributes to the difference in similar way, where the deep ocean delta C14 changes are within the range of plus or minus 1 per mil in both natural and total radiocarbon, and which indicate the changes are negligible. Also, the changes occur mostly in the shallow reservoir for both natural and total radiocarbon prominent between 26 and 27 isopicness. Also, the change in total and natural C14 distribution due to forcing differences in the Atlantic are weak compared to the Pacific. Compared to the Pacific, the 26-27 isopicnal changes are not quite prominent in the Atlantic region. However, it is mostly prominent in the northern mid-latitude and that extend from surface to the deep ocean. And the natural C14 difference remain 0 to 2 per mil over time in the tropical ocean. Also, the changes occur in the northern mid-latitude and south of 60 south indicated variability in the ocean transport are strong in the surface to the deep in the Atlantic Ocean. Now the summary: the model captures large-scale structure and large range of delta C14 values, both spatially and temporally, suggesting that the uptake of Uptake and the transport of C14 are well represented in NEMO. Modal biases are large in the high latitude, indicating that the model is inefficient in transport of the model and that causes C14 to accumulate too much near the surface and produce high delta C14. The rate of change of C14 in the decades over the decades occur rapidly in the observation, but in NEMO it is weaker in the shallow and deep reservoir, indicating that model is too efficient in dispersing C14 within the interior ocean. And the separation of shallow and deep reservoir occur between around 26.5 potential density surface in the Pacific, as shown with the previous studies. However, it has shifted to higher densities in the recent decades. The difference between the model simulations, the JRA neutral air and the JRF host simulation shows that the large variability occurs between 26 and 27 isopycnals in the Pacific. However, it is mostly prominent in the mid-latitude in the Atlantic, and the differences are plus or minus 15 per million for the total radiocarbon and plus or minus 6 per mil in the and for the natural radiocarbon, which is associated with the ocean dynamics, change in ocean dynamics and air-sea exchange due to variable atmospheric forcing. With that, I end the talk. Thank you for listening.